The next WebAssign is, so what we did last time, if you remember, and where I'm picking up from, is we had this so we have an integral that you, for whatever reason, cannot or don't want to calculate the actual formula for. A lot of integrals are that way. I gave several examples. And so you want to do this numerically. And really, we have three methods of choice. There are more, but we have the trapezoid rule. We have the midpoint. Then we have Simpson's method. I don't know why one is a rule and one's a method, but okay. We'll call it Simpson's rule. Let's not even give them methods. Or we have trapezoid, midpoint, and Simpson's. And I went through this last time. The trapezoid, you fit things like this. That's supposed to go under. Oh well. You fit trapezoids underneath and you add up their areas. The midpoint, you fit rectangles underneath. Rectangles, they don't go underneath, they go through their middles. Come on. Like that. And then Simpson's, which I can't draw very well, you go through 3 points per thing, and you put little parabolic guys on top. There's a formula for them. The trapezoid one you evaluate here and here, the heights, and you average. Here and here, the heights, and you average. The midpoint, you average, and you evaluate in the middles. And Simpson's, you take one of these, 4 of these, and 2 of these, and you add them up in that way. If you look at the formula, let's call this Tn, Mn, and this one is S, and I'm going to call it S2n because of this issue that, well, just I will. We use sort of more points, depends on what you call n. Then, in fact, Simpson's rule, if you just look at the formulas that you get, which I didn't say last time, Simpson's is just 1/3 of the trapezoid plus 2/3 of the midpoint. I didn't clean enough room. Try this again. So if I calculate the midpoint method with 5 rectangles and the trapezoid method with 5 rectangles, and I take my answer and I take 1/3 of this one and 2/3 of this one, then that would give me Simpson's with 10. That's backwards, isn't it? No, that's right. Isn't that backwards? It should be Simpsons with fewer. Does anybody have a clue what I'm talking about? Okay, well then you should have stopped me like 10 minutes ago. All right, so this you understand, right? I don't need to review this again? Yes? You don't understand. Okay. Well, if you shake your head, it means no. So, unless we're in India, and then it means yes. All right. So, okay. So, I think that's right. Anyway, if you just look at this, you see if I take this guy and I take 1/3 of the answer that I get from this rectangle, and I take 2/3 of what I get by just evaluating at the middle, then that should give me something about this, this, and this. But the numbering here is a little bit funny because the way we use the number n does not count the number of rectangles, it counts the number of points for Simpsons. So this is right. Okay. Does anyone need me to write down the formula again? Yes? Just figure them out, they're easy. Okay, so the trapezoid with n is, so we take the width of the little interval, so I'm integrating from b to a to b. So I take the width of each little rectangle that I take, and then I want to average. So I pick my n points going, it's really n plus 1 because I start at 0, and I evaluate my function at the first point, at the second point, and at the last point. So here I have n plus 1 points. This is the heights on the rights and the lefts of each rectangle, and I'm going to average them, so I have to divide by 2. And I'm sorry, I take twice those. All the guys in the middle. The reason they're double is because when I have a trapezoid like this sitting next to a trapezoid like this guy, whose height is f of x1, gets counted twice. So I get a 2 for everybody in the middle because you count it from the right, you count it from the left. In the midpoint, again, I take the width of my rectangles, and now I just take the heights. Let me call them m's instead of x's. So in this picture, I'm not going to have room for Simpsons. Here I have xn, or not n. I have my interval. I chop it up into a bunch of rectangles, and I call this side x0, x1, x2, until I'm done, xn, like that. And I'm going to call m1, m2, m3, mn, the midpoints of those rectangles. So, okay. And then the heights over it are plug this into the function. The midpoint formula is just take the width of each rectangle, this distance here, is b minus a over n. It's a really terrible race. B minus a over n. That's the width of each guy. For trapezoid, I have to average. For midpoint, I just divide. But the thing that's annoying about midpoint is I've got the numbers are ickier because I have to divide by find midpoints. And then for Simpsons, which I didn't leave room for, right here. For Simpsons, I'll move over. I'm going to use that same notation, and now, just due to convention, if I have, this is Sn. Then again, this is 2. Sorry. Here, I have about n points. I'm going to use exactly the same points. And what I want to take is the width here. And then I'm going to average these two things in sort of a funny way. So I'm going to take the function at the extreme right side. This side. Is that right? I don't know. way over there, the lowest value. And then I'm going to take 4 of the midpoint. And then I'm going to take 2 of the left side, which is also a right side. And then I'm going to take 4 of the next midpoint. And then I'm going to take 2 of the next side. There's F's here. And 2 of the next side, and so on. And then when I get to the end, I will be taking 2 of the last guy plus 4 of the last midpoint plus just 1 of the last point. And then this averaging that I'm doing, because I have sort of 3 points for each rectangle, instead of 2 points for each rectangle here, they're not rectangles, each interval, I divide by a third. Because when you average 3 numbers, you divide by 3. When you average 2 numbers, you divide by 2. And if you look at these formula, you can see that this guy is just, well, if I double the n, this guy is just that guy with fewer plus that guy. Backwards. That was a lot of discussion for something not really very worthwhile. But, okay? Yeah? Do you want to use Q's or smiley faces or rabbits? Use whatever letter you happen to like. The reason that I switched from X's to M's is if you think about rectangles, if I think of this as a rectangle, I have a right side, a left side, and a middle. So I use right and left for X and M for middle. But if I'm thinking of twice as many points, these are all the same. Use whatever letters makes more sense to you. The process, so I will go through one more example of this. Yeah. So, the reason it's 4 and 2 and 4 and 2 and blah, blah, blah is because I want to count the middle more. You can, and I just should have done it, I really don't have time, is I want to find a parabola going through 3 points. When I'm finding a parabola going through 3 points, the middle counts more than the 2 sides. That's why it's 4 and 2. The middle is twice as important as the 2 sides. And so, and because everything's double, that's why it's 4 and 2. But you could just, if I just solve the equation, I don't think it will help. So, and it'll take about 15 minutes, so I don't want to do it, because I'm already late. Okay? So it's just 4 and 2 and 4 and 2, and I'm sorry, that's not very helpful. Okay. That's not what I'm talking about today, too bad. We have these bounds on the error that tell us how good these approximations are, which I, of course, have not memorized, and you don't have to memorize, but the error, so let me just call it, no, I don't, yeah. So, E sub t, which by that I mean the difference between the trapezoid and the actual value. So this is always less than the width of the interval to the third divided by the number of points you're using squared, and I think this is the 12 for the trapezoid. That means that's how far off the trapezoid is. No more than that. It could be exact, but it's never more than, and there's a constant. Sorry. This constant is the maximum of the second derivative over the interval. I'll do an example of this in just a second. The error on the midpoint, well, it's not the same. Is less than the same thing, e minus a cubed k over 24 n squared. And Simpson's rule is magic, because Simpson's rule, for twice as many evaluations, you go from a square to a fourth. So I'll just write it here. For Simpson's rule, this is less than b minus a to the fifth, and then this constant here, I used k, so I'm going to use m, over 180 n to the fourth, where here m is the maximum of the fourth derivative. Okay? So, what does this mean? Now I'm going to do an example. So suppose, let me do an example with Simpsons, because that's maybe the most complicated. And rather than doing some integral I can't do, let's do something I can do, but only with a four-function. I'm going to do it sort of by hand. So suppose, for some reason, I don't know why, you only have a four-function calculator, or you can only multiply, and you want to calculate the log of 2. How good should I want? 3 places? 4 places? Should I do log of 3 instead? Let's do log of 3. Doesn't it? Does anyone know the log of 2? Is anyone here? Okay. So, I can only use addition, multiplication, and division. I guess I could subtract if I need to, but that's really addition. And I want to calculate the log of 2 to 3 places. What do I do? Nobody knows? It's impossible? I take out my calculator? Yeah. Right. 1 to 2. If I integrate, it's 0 left. I get a problem. So, I know that the integral from 1 to 2 of 1 over x dx is the natural log of x evaluated from 1 to 2, which is the log of 2 minus the log of 1. And one of the things that you're supposed to know is that the log of 1 is 0. So that's the log of 2. So, that's nice. I know that the logarithm is the integral of 1 over x, and so now I have a formula. But I only get to use addition, multiplication, and division because the log button on my calculator broke. And so, or I was thrown back in a time machine, and it's the 17th century, and we need to calculate logarithms because Isaac Newton just asked me, and what do we do? Okay, so now we can do this. Now I want it good to 3 places. So I'm going to use Simpson's rule because it's really the most efficient. I don't want to do too many multiplications and divisions. So I know Simpson's rule is going to be the least amount of work for me. So what do I do next? How do I know whether I use n equals 5, or no, n equals 10, or n equals 100, or n equals 4? How can I know? All the required information is on the board. So what do I do next?
You graph.
Draw the graph, okay. Here's the graph, 1 over x. I want to go from here to here, 1 to 2. I want that area. So I suppose I could cut out a lot of little pieces of paper and measure. Getting that to 3 places, probably I'd have to draw the graph exactly to about the scale of this room and then measure. Or I can use a micrometer, but I don't have a micrometer, so that's not going to help. Okay, so you had someone started to tell me another. Maybe I'll draw a bigger graph. So, what's next? The information is on the board. Everything you need. You just got to do some calculation. Yeah. Okay, so suppose I just picked a value for n. Pick a value. 10? 4? Okay. Suppose I pick a value for n and I do it. 4. I get an answer. I have to have it right. Because if it's not right to 3 places, my aircraft will crash. My bridge will fall down. Whatever it is I'm doing will not work. So I have to know it's right. But I don't know the answer. And I don't have a calculator that can tell me the answer. So I could just pick and hope beyond hope that I was lucky. I could pick n equals 1,000 and sweat a lot, and then later only to learn that 2 would have been enough. And maybe 1,000 wasn't enough. Maybe I needed 2,000. Sorry? Somebody just said it. Use the error. Right. So I know already, right here, from this formula, how to figure out how good it's going to be. I got to do some division and junk, but this formula tells me. So, lucky for me, A is 1, and B is 2. So B minus A to the 5th, so my error, my Simpson's error, is less than 2 minus 1 to the 5th power. Well, that's easy. There's a number m that I don't know yet. 180, I know what 180 is. And n to the 4th. And I want this error to be less than, I want it good to 3 places. So I want this less than 0, so this is what I want. 0.3 places and then round. So one thing here is when I say good to 3 places, I want the 3rd digit after the decimal point to be correct. That means that I can have a mistake in the 4th digit after the decimal point, but it can't be bigger than 5. Because if it's bigger than 5, I'll round the wrong way, and my 3rd digit will be wrong. So I want my error to be less than 0.005. Okay? Is everybody okay with that? So now I just need to figure out what n is, and then I have an equation for n. Okay, so what's m? Well, m is the maximum of the 4th derivative. Yeah. It's 180. I wrote 120 and then I checked and it was 180. I changed it at the very end of the class. It better be 180. Let me check again because... So you may have noticed I'm not really very good with actual constants. It's 180. I have a very terrible memory for numbers. I'm actually not very good at adding and subtracting either, but... Okay, so here we are. I'm terrible at math. I'm actually pretty good at math. I'm just bad at arithmetic. Okay, so here we are. So I have to figure out what m is. So m is the maximum of the 4th derivative. Well, that means I need to take some derivatives. So f of x is 1 over x. The first derivative is negative 1 over x squared. The second derivative is negative 2 over x cubed. The third derivative, negative 6. No, it's positive now. Over x to the 4th. Oh yeah, this one's positive. This one's negative. I don't care because I'm going to take the absolute value, but okay. And f to the fourth is positive again. It's 24 over x to the fifth. And now, so this is a function, but I want a number. And I want the number here that makes this the biggest. The graph is a little screwy looking. I want the number between 1 and 2 that makes this the biggest in absolute value. So I want x to be 1, because it's 24 when x is 1, and it's 24 over 32 when x is 2. So 24 is bigger than 24 over 32. So that means I take m equal to 24. Now I can get a useful answer even if I can't figure out exactly what the maximum is, as long as I take something bigger than it. So if I wanted, I could take m equal 100. And I would get something that would work, but maybe I'd do extra work. So I'm going to take m equal 24, but then when I do my calculation, I may change it to be big. Okay. M is 24. And so now I need to solve I need to find an n so that 1 over 20, forget about the 1. 24 times 1 is usually 24. 24 over 180 n squared is less than 0.0005, which maybe I can write as 5 over 1. Thank you, that's a 4. 5 over 10,000. Is that right? That's right. So I need to solve that. So that's the same as saying n to the fourth is bigger than 24 times 5 over 180 times, something's wrong here, my 10,000 and my 5 are on the wrong side. 24, 1, 2, 3, is it 10,000? Yeah. Oh, I see, I did 2 places in my office. Okay, 24,180 times 5. Okay, so let's see. We can reduce this a little bit, I suppose. I don't know. So, of course, if we have a calculator, we can just calculate it. Are we in the 17th century or are we in the 21st century? We switch. We can go back and forth. Does somebody want to calculate this for me? No? Nobody has a calculator? So if I, 80 over 3. Okay. So 80 over 3, this is about, well, so let's call that 90 over 3. So that's less, so this equals 80 over 3. This is 90 over 3. So I'm going to call that, wait, I went the wrong way. All right, 80 over 3, which is 20, 30, what's 80 over 3 goes into 80 2 times, and then 3 goes into 20 7 times-ish. So this is 16 and change. Okay. Yeah, what are those numbers? 26 and stuff. And so I need to find a number n whose fourth power is bigger than 26. Well, let's see. The fourth power of 2 is 16. No, 2 isn't going to work. The fourth power of 3 is 81. 3 works. I'm cool. So here I take n equals 3. Oh, but it needs to be even. But since we're going to do Simpson's method, I have to have an even number of rectangles, so I better use so I need n equals 4, because Simpson's rule doesn't work with an odd number of n. So that means 2 intervals is good enough for Simpson's rule to give me the log to 5 places. So that means I need to calculate with 5 points. So I need to take the inverse of 5 numbers, add them up, and stuff. So I might as well finish that, completely blow the entire class. That's always good. So it's good because the other lecture, she's behind, and so now we're behind too. No, but I write the test so that I can do it without a calculator. And if I can do it without a calculator, you can for sure do it without a calculator. So there's a lot of things that calculators are useful for, and I carefully choose the numbers so that you can do them without. Okay, so we do n equals 4. I might as well do n equals 4. So for Simpson's rule with 4, I'm going from A to B. That means the width of each of my rectangles is 1/4. So I have 1/3 times 1/4. And I'm going, remember, from 1 to 2. And I'm going to find 4 points between 1 and 2. The first one is 1. The middle one is 1.5, which is called 3/2. The last one is called 2. And then the middle between 1 and 3/2 is 1.25, which is, 5/4. And the middle between 3/2 and 2 is 7/4. Okay? So those are the points. Those is my x0, m1, x2, m2, and x. What? No, this is 1.5. This one is 3/4. Halfway between 1 and 1.5 is not 3/4. Half of 1.5 is 3/4. It's 1.25, which is 5/4. Or if you prefer, 1 plus 1/4. And this is 1 plus 3/4. Yeah. Okay, so now we do the stuff. We add up the function evaluated here. That's easy. 1/1 is 1. Plus 4 times the function evaluated here. So this is 4/5 because my function is flip it. Plus twice the function evaluated here. Plus 4 times the function evaluated here. Plus just 1 of the function evaluated there. And so that gives me my approximation. And let me not do the arithmetic because I'll blow it. Yeah. Because my function is 1/x. So if you prefer, you just add another line. So this is 1/12 of 1 plus 4 times 4/5 plus 2 times 2/3 plus 4 times 4/7 plus 1/2. Because my function is 1/x. Where did you go? There you go. So my function is 1/x. So that's right. And then this is some number. So, you can do this arithmetic. I will blow it, so I'm just going to stop it. Yeah. So I feel confident that you could do the same thing if I asked the question with trapezoid. Right? You would not feel they could do this with, say, trapezoid or midpoint. It's the same process, but you only need the second derivative. So my constant k for trapezoid or midpoint is 2. But I'm only taking the square root instead of the fourth root, so it's a bigger number. Okay, it's something like 20. Some number like that. Maybe it's 40. Okay, so let me just start the next thing. So I'm going to ask a different question now, and I was all set up to do quickly, but so any questions about this? Or are we good with this? Yeah. Depends on what you want to count. So if you are counting the number of intervals, see, notice that in Simpson's rule, I have 2 things with parabolic tops, but I have 4 points. So it depends on who you talk to. So the book's author prefers to count the points. I think if you read the Wikipedia article, it prefers to count, if it's not Wikipedia, it's some other one. It prefers to count the number of intervals. And so in this case, the n I would call it 2 intervals, or n equals 4.
The number of points for that number.
Yes. That's what to change the formula, if n is the number of intervals, then instead of the third, it's a 6th apple fry, and you have more stuff inside. But okay. So, depends on what you want to call n. Oh, shoot. So here, yeah, this is it, 2n. Yeah. The formula is 2n. Yeah. Yeah, you might be right. Yeah, but that's it. No. Because I'm not counting these. I'm counting yep. So, that number, b minus a over 100 is not the width of the interval, it's the distance between the points. Right? That's why it's a 2n. It's really a 6 and if you think of it as the distance between the points, then it's b minus a over 2n. That's putting 2n points in there. In this case, the distance from here to here is 1/4. Distance from the first point to the next point, which happens to be a midpoint, is 1/4. So I divide by 1/4. This is right. Okay, let's move on, because I'm really sick of it. Suppose I look at 1 over x. Well, let's do 1 over... Let's do e to the minus 1. Suppose I'm looking at the integral of e to the minus x dx. I know it looks like sextants, but okay. I'm doing the integral of e to the minus x dx. Graph of e to the minus x looks like this. And it goes way out. It gets really small here. Did I fix my... Is it off? Probably I can't. Probably the battery. Nice. The battery's dead. So I just have to talk like this now. Okay, because we only have 5 minutes, so I'll shout for 5 minutes. It's fine. So I'm doing an integral like this. Now, suppose I start at 0 and go to 10. Then this gives me minus e to the minus x evaluated from 0 to 10, which is minus e to the minus 10 plus 1. Because minus e to the minus 1. Yeah, that's right. Well, write it out. Plus, so really, minus e to the minus 0, which is 1 minus e to the minus 10. This is a tiny number. Suppose instead of going to 10, I go to 100. It's an even tinier number. So, it actually makes sense to say that if I let this go forever, I never get bigger than 1. So, the statement is, am I still shouting loud enough? Yeah. Statement is, that here, for any, let's call it m bigger than 0, the integral from 0 to m of e to the minus x dx is always less than 1. In fact, we know what it is. It equals 1 minus e to the minus m, which is always less than 1. But as m gets bigger and bigger and bigger, this goes to 1. So we take the limit, m goes to infinity of this integral, you get 1. That means we can make sense of the integral from 0 to infinity of e to the minus x dx. You can say that's 1. That means if I had an infinitely long shape like that, I could always, and I need 1 gallon of paint to paint one square unit, I could paint it with 1 gallon, even if it's infinitely long, because it gets so skinny. So we can make sense of this. And it's not just e to the minus x that we can make sense of this for. We can make sense of this for other functions as well. So such a thing is called an improper integral. And maybe it's improper if you... Oh, I put bounds on it, now it doesn't look like sex dx. It was improper if we do the other one too, because it was just not polite. Okay, so we have this improper integral here. So an improper integral means that it's infinite in width. So in general, we can make sense of this notion of improper integral if one of the bounds is infinite. So in general, so we define the integral from any point to infinity to be the limit of take the limit as the upper bound goes to infinity if it exists. If it doesn't exist, that limit doesn't exist. So, for example, the integral from 0 to 1, of 0 to infinity of x, well, let's add there. Let's go from 1 to infinity. The integral from 1 to infinity of x dx, this limit doesn't exist. It becomes infinite. So we would say that this diverges. And we would say this one, if it exists, it converges. This word diverge and converge, we're going to use a lot in this class. And you should get used to these terms now because in about 3 weeks, we'll be using them a lot more. So, if a limit doesn't exist or is infinite, we say the integral diverges. Probably a good place to stop. So, we'll do more of this stuff on Monday.